Hello everyone, welcome back to the channel the Univ ScienTheta. As mentioned earlier, this is the part of our ongoing series exploring the world of integrated circuits. Today we'll be diving into the continuation of Moore's law. But before we get into that, let me give you a quick recap of what we have covered in the part 1. Moore's law, the truth behind semiconductors. We've explored the significance of Moore's law, its brief history, what it actually states, and how it has evolved over time. Now let's pick up where we have left. I know it took a bit of time for this continuation to reach you, but with the priority of delivering the maximum quality, sometimes I guess it's okay to compromise on the deadlines. A major question that often arises is, why can't we continue scaling down transistors at the same exponential pace? Why do we need to redefine Moore's law? What exactly is obstructing the pace? In an ideal world, everything would follow theory perfectly, but real world physics introduces complexities. The goal of every physicist, mathematician, and an engineer is to bring theory into practice, to turn ideas into reality. However, in real world, we face several challenges like resistance, power dissipation, leakage current, area limitations, and manufacturing costs, all of which slow down scaling. For example, until the 45 nanometer node, reducing the MOSFET gate oxide thickness, which was typically silicon oxide, worked well. But as we scaled further, quantum tunneling became significant, increasing leakage current. To tackle this, high-K dielectrics like hafnium oxide replaced SiO2. Thankfully, it worked till some more lower nodes. Yet, even that had its limits. That's when FinFETs emerged, introducing multi-gate structures to control the channel better. Like that, technology has evolved. Now, to keep Moore's law moving forward, we need entirely new fields of exploration like quantum computing, nanophotonics, and neuromorphic engineering. Without innovation, Moore's law will inevitably slow down and may eventually die. Pessimistically speaking, we've reached a point where scaling below 1 nanometer is approaching insane levels of miniaturization, making manufacturing extremely difficult. Even with the most optimized fabrication environments, particles smaller than 1 nanometer become nearly impossible to eliminate. This is why we had to evolve from traditional 193 nanometer photolithography to 13.5 EUV, extreme ultraviolet lithography. While these advances allow continued scaling, they also significantly increase fabrication costs. And that brings us to a crucial realization. Moore's law, apart from a technological law, it was also a business model. So shouldn't be the cost of primary factor of concern? Absolutely.
True.
Now let's talk about Dennard scaling, a concept that played a key role in enabling Moore's law. Back in 1974, Robert Dennard at IBM proposed an idea. As transistors shrink in size, their power density remains constant. In simple terms, this meant we could make transistors smaller, faster, and more power efficient, all at the same time. This was a game changer. But by 2003, things changed. Dennard scaling effectively came to an end. But why? Because as we pushed for higher clock speeds in microprocessors and memory, we started running into physical limitations, more heat, more leakage, and power issues. The transistors could still get smaller, but they couldn't maintain that ideal efficiency Dennard talked about. So why did Moore's law continue where Dennard scaling didn't? That's the interesting part. Dennard scaling was in strict mathematical principles which didn't leave space for flexibility, while Moore's law was described in an imprecise language, leaving the space for engineers and technologists to reinterpret and save the law over time. Think of Moore's law not as a rigid formula but as a fluid idea. It doesn't just die, it reshapes, reforms, and continues to inspire innovation. It's not just about how many transistors fit into a chip anymore. It's a symbol of how fast computing can evolve and how deeply it can impact innovation, industry, and the economy. Looking ahead, the future of semiconductor technology is filled with exciting possibilities. According to the International Technology Roadmap for Semiconductors (ITRS), which uses the scope of Moore's original paper as a baseline, the future won't just be about squeezing more transistors into a chip, but about exploring entirely new paradigms beyond traditional CMOS. We are talking about next gen technologies like neuromorphic circuits that mimic the human brain, quantum computing with qubits instead of bits, tunneling FETs, negative capacitance transistors, Spintronics, carbon nanotube transistors, and even Josephson junctions for ultra low power superconducting logic. There's also been a shift in chip architecture since around 2015. Instead of just making single core processors faster, the industry developed multi core processors with higher transistor densities. Even the way chips are assembled has moved from flat 2D layouts to 3D chip stacking. Technologies like high bandwidth memory (HBM) and hybrid memory cube (HMC) are now enabling multiple DRAM chips and a CMOS logic die to be stacked into a single powerful module, boosting performance while saving space. This shift isn't just about keeping Moore's law alive, it's about redefining the path forward for computing power in a world that's becoming increasingly data driven and AI heavy. Every advancement from now on might require significant discoveries and inventions across physics, biology, and computer science, or even maybe a new miracle every 2 years. The real hard work is just beginning, and that's exactly what makes this the most exciting time to be in electronics and computing. Back in 1956, IBM launched the 305 RAMAC, the first computer with a hard drive, and it weighed over a ton. That hard drive, which has to be lifted into a plane with a forklift, just stored 3.75 MB. By today's standards, that's nothing. Due to decades of reliable exponential growth powered by Moore's law, computers have become smaller, faster, and cheaper. Moore's law isn't just a physical or a natural law. It's a powerful prediction, a perception. Transistors are the reason we have advanced at such an exponential rate. But what exactly are transistors? And why is silicon the element of choice when there are so many other elements available? We'll dive into these in the next video. Because electronics is all about using electrons to control electricity, and the most advanced transistors today can control individual electrons. So just imagine how small they are. But here's the final question. Why even aim for exponential growth like Moore's law suggests? Why not settle for linear progress or just stagnate here? The answer lies in one simple truth. Our demands are growing exponentially. If we don't move forward at the same pace, we'll fall behind badly. Think about it. We are 8.2 billion people on this planet, carrying over 20 billion mobile devices, interacting with more than 100 billion intelligent agents every single day. And we are not just browsing memes. We are solving problems as big as food, water, education, employment, and sustainable living through ICs. But here's the challenge. The power available from our grids is limited. Yet the data we are generating is growing exponentially than our ability to convert it into information. Any linear response to an exponential problem will always fail. In 2022, Nvidia CEO Jensen Huang boldly declared that Moore's law is dead. On the other side, Intel CEO Pat Gelsinger opposed it. And in that debate lies the spark that keeps the semiconductor race alive. Because in the end, Moore's law is more than a rule. It's a mindset to push boundaries and keep the world moving forward. There is nothing in science like we'll wind up everything using one trick, No moment where we say, that's it, we figured it all out. The search for scaling up our computational power must continue, pushing the boundaries of what we think is possible. Yet physical limitations are starting to push back, forcing us to ask, how much further can we really go? But remember, any idea, just like Moore's law, can bring a revolution for decades. So let's just keep exploring, questioning, and unveiling the mysteries of science and the secrets of the universe to drive technology and humanity forward. Like, share, and subscribe to the Univ ScienTheta for more such content. See you in the next one.